All right, let's just do a little recap. All right, let's do a recap. So binomials. All right, so this is a binomial that represents a coin toss, and this is actually a replica of the same three diagrams we saw on the very first day of class so long ago. These are the probability distributions for more coin tossing. Right, so n equals 10, n equals 32, n equals 100, and so far we've described two theorems that will bound the sum of the tail. And why do we care about the sum of the tail? The further we stray from the mean, we would like to say this is not likely to happen, right? How unlikely is it to happen? Well, it sort of looks like it's mildly probabilistic for n equals 10. N equals 32, it almost looks pretty close to 0. There's a little bit of thing that's registering on the diagram. And for n equals 100, it's really not likely at all. The theorem that we're using is Chebyshev's theorem. If you look at the denominator, right, it says the variance of x squared is on the numerator divided by x squared. X squared is the distance from the mean. Okay, so the convergence rate for as x goes up is it converges like 1 over x squared. Okay, that's pretty good, right? The drop off is pretty steep, but this turns out to be much steeper than 1 over x squared in real life. This is why we get these bounds that are over here that are not as close as we would like. Anyway, this was enough to solve our problem, and the lesson here is that the more times that we toss a coin, the more likely it is to converge towards the mean. Okay, so it's going to get tighter and tighter and tighter, and we can use that to solve problems like this, like how many times we have to poll a group of people and ask them their opinions before that opinion converges towards the true value of p. And given some parameters, epsilon and delta, our confidence interval and confidence level, we can tune our study as much as we like. We came up with a number, okay, so 62,500 samples will get us within that confidence level. Okay, so, and you'll notice there's epsilon squared is in the denominator. It drops off as a square. Okay, so this convergence has little to do with how big the population is. It has everything to do with how many times we sample. This is starting to sound a lot like something that we have been told early on in life, but I'm going to not use that name explicitly, at least not written down, but it's called the law of averages. Okay, and I'll talk a little bit about that and compare it with the language that we are using here. First of all, there is a convergence theorem, okay, that says that if you have a whole bunch of samples that you take n of them of the same thing, all right, so G1, G2, they all behave with the same distribution, they have the same mean and the same standard deviation. Okay, so these are known. If you define S at n to be the sum of all those and take the average will converge towards the mean. Okay, so this says that the distance from the mean, the probability that the distance from the mean exceeds epsilon is this value over here, 1 over n times sigma divided by epsilon all squared, which grows as 1 over epsilon squared. Okay, so what this means is if you have a whole bunch of samples, you take n of them, as n increases, the probability that you deviate much from the mean will decrease, and it will decrease according to this book. Proof. We just compute the probability using Chebyshev and the variance of Sn over n. Okay, and Sn over n is the sum of all of these individual things. The expectation of that is clearly mu. The variance is going to be the sum of all the variances of each of these. Now, why is that? It's because they're independent. Okay, so the variance is just add. There is one small gotcha in that we're dividing by n, and anytime we multiply by some constant, like 1 over n, we pull out the square of that. Okay, so the variance of S of n equals the variance of G1 through Gn, so this is the sum of all Gi's. I equals 1 to n, I guess. And the variances add because they're independent, so it's 1 over n squared, the sum of all the variances. And the variance here is sigma squared. There are n of them, so that's going to give us n sigma squared divided by n squared, which is sigma squared divided by n. Okay, so we've computed the variance here. We applied Chebyshev. Okay, so the probability that Sn over n minus mu, okay, so the difference between the predicted mean and the mean is far from its, far from its true value. So for some small epsilon, it's less than or equal to the variance of the quantity divided by epsilon squared. And we just plug this in. So that's sigma squared and epsilon squared. Okay, so it just drops out from the theorem that we did before, and just to verify that this is indeed something that we could apply to the voter poll, we can. Okay, so this what was the thing? We had epsilon already. Okay, so we just needed sigma squared for each of the poles, right? And the variance of each of the poles was P1 minus P. Okay, so we plug that thing in there, and we get this thing back up here. All right, so that's the same, and then we approximate the P1 minus P to a quarter. So that was the next step. But yeah, it indeed matches these two things. Okay, so indeed, the more you sample, the closer you are going to get to the mean with reducing, shrinking probability. And this is sort of like how the law of averages sounds to you, right? Okay, so remember the law of averages, what they told you back in gambling school when you were in grade 3, right? That if you roll a die a whole bunch of times and you get a bunch of 6s, then the chances are going forward that you're not going to get a lot of 6s coming up because they've already had their 6s, right? No, it's not true, right? Each die roll is supposed to be independent of the other ones, right? Okay, so it's not that you're 100 ahead in heads, so the tails are likely to come, but over time, if you keep on tossing, it will converge to the true value of 50-50. Is the same thing as regression to the mean? No, that's a different thing. That's when you're trying to fit a curve to data. So you're trying to minimize the sums of errors there. So this is convergence to the mean. So okay. So anyway, law of averages is this is as close as we're going to get in this course. The weak law of large numbers. Okay. So if you have n pairwise independent random variables, you take the average of all of their results, and they have the same mean and standard deviation, okay, so that we can apply the theorem on the previous page. Then the limit as n tends to infinity, so the more you sample the convergence of this thing for every epsilon greater than 0, you can get it as tight as you want. It will converge with probability 1. Just a quick proof, this follows directly from the previous page. Okay, so if you were to take the limit as n tends to infinity of this quantity, okay, so we'll just put that in brackets, so the probability that difference between xn and mu is less than or equal to epsilon, okay, this must be greater than or equal to, the limit thing doesn't change, we just wait for it later, this is going to be sigma squared over n epsilon squared. Oh, wait a second, this is less than or equal to, so the other one was greater than, so this should be 1 minus. Yeah, it's not going to hurt us here. Yeah, should this be strictly less than? I mean, it's not going to hurt. But yeah, sure. Okay, so this is going to be greater than or equal to 1 minus, yeah, okay, sure, that's fine, less than epsilon. Okay, so this is the complement event from what we had on the previous slide. Okay, and as n tends to infinity, this thing tends to 0, so this is equal to 1 minus 0, which is 1. Okay, so as you toss coins, if you get 10 heads in a row, you might want to check that you're not dealing with a two-headed coin. But if the coin is fair, every trial should be independent, and eventually it's going to converge to 50-50. And if you toss a million times, with 100 more heads than tails, it's maybe a little aberration there, but you're probably eventually going to get back to 50-50. It's not saying when though, right? It's not going to be immediate. This is why casinos are in business, which is the note down here. Okay, so if you like going to the casino, every bet that you make at the casino, the house has odds against you. So it's not a lot of odds, but it's enough odds that they can stay in business for a long time and take n bets as n gets large. Okay, so eventually it's going to converge to winning for them as long as they have enough money and enough time. So if you hit it big at the blackjack table or a slot machine pays out and you're $1,000 ahead, go home, keep the 1,000, don't ever go back to the casino because you will eventually deal it back. Okay. Now, as I mentioned, these binomials have a pretty steep drop-off, and most of the real distributions that you deal with also have a steeper drop-off than 1 over x squared. Okay, but if that's all you got, that's all you got. Okay, so if you only have the mean, you can only do Markov's. It's a drop-off of 1 over c. It's not even as good as 1 over c squared. If you add in the variance or the standard deviation, you can get a 1 over c squared, basically. As you get further away, you can predict this with 1 over c squared, which is better. And this happens in a lot of cases, but if you have a whole bunch of variables that are mutually independent, this is asking a little bit more, and they're bounded between 0 and 1, then you can bound by an exponential using one of two Chernoff bounds. Okay, these are the last bounds I'm going to teach you in this course, but they're very powerful when you kick them in. Okay, so here's the first one, and you're responsible to know these, okay, and apply them in the right situation. And the first one is a special case. All right, it is a binomial that is exactly centered. And so the coin tosses are 50-50 every single time. So if X is a binomial distribution of n tosses where it's a fair coin, then for any t up to root n, and the reason it's root n is just to keep these things within bounds, if you go t standard deviations above the mean, and the standard deviation is root n by 2, or t standard deviations below the mean, you can compute the tail, or bound the tail by an exponential that grows as e to the minus t squared over 2. We're going to see how fast this grows in just a sec. Okay, this is a symmetric bound, and I just want to let you know, because we're going to try the other bound using the same technique, because it also works on this case. It's worse than this. So if you ever are faced with a binomial that's exactly symmetric, or you can transform the problem into a binomial that is exactly symmetric, you should do that and use this bound. It'll work out better for you than using the other bound, which I'll show you in a few minutes. Okay, well, let's give this a try. Okay, so another do-over. What is the probability of being 1/4 of an n away from the mean? Okay, so what is it? Well, we're going to use the Chernoff bound. Okay, we're going to use this one for a specific t, and we have to solve for t. So that's one of the key steps, and then we just sub in for t and draw our conclusion. Okay, so we're going to use the Chernoff bound 1. Okay, so we want the probability of z greater than or equal to 3/4 n, and we want it to look like this. Okay, the difference here is 1/4 n. So if we want it to look like this, it'll be probability of z greater than or equal to n by 2 plus another quarter n. And then we want to look like this, right? We want to find t so that when you multiply t by root n by 2, you get n by 4. Okay, so what do we need to multiply by? It looks like another root n by 2. Okay, so just putting it in the form that we need, so it's going to be t times root n by 2, where t is equal to root n by 2. Okay, so we're trying to make this look like this. Okay, so it's just a little bit of working, and you have to do this with every problem that you're faced. Okay, so any bound that you need to make it look like the Chebyshev thing, or make it look like Markov. You have to make it look like Chernoff. Okay, and all it says is that this is less than or equal to e to the minus t squared by 2. So that means the probability z is greater than or equal to 3/4 n is less than or equal to e to the minus root n by 2 squared by 2. And you multiply all that out, and you get e to the minus n by 8. Now this is for general n, and we have 3 cases here. N equals 10, the probability that we're looking for is around 0.287. That's pretty bad. Just for context, 28.7%. It's not as bad as Markov, but just to give you context here, it's way worse than Chebyshev. And you'll find this. For small n's, you'll find that Chebyshev often beats Chernoff. Okay, so the actual, I'll just put the actual over here. Okay, so the actual value of the tail is around 5%. N equals 32. This is around 1%, 2%, I guess. The actual is less than 1%. And just to show you, oh, sorry, maybe I got this wrong. Sorry, it was 1/5. Sorry, the actual was 0.55. So the one from Chebyshev was 1/5. That's 20%. Okay, still, it's better than what Chernoff gave, but here it's way better. 1/16 is about 6%. Here it's a way better estimate. And n equals 100. The chance that you toss 75 or more heads is 3.72 times 10 to the minus 6. So that's on the millionth scale. Chebyshev was 1/50, so that's 2%. So the actual is 2.8 times 10 to the minus 7. And maybe that makes some good sense. Maybe this is, this is following this pretty well. Maybe it makes some good sense. If you look at this e to the minus t squared in the function, the Gaussian function, which does approximate a binomial for large n, has a e to the minus x squared in it. Okay, so it's got a similar shape to it, and here the drop-off is similar. It seems to be following it pretty well as n gets large. Okay, so that's Chernoff bound 1, special case, okay, symmetric binomial distribution. Okay, questions about that? Good? Okay, I'll show you the other one, and then we're going to compare the two, all right? I'll just keep these close by. Okay, Chernoff bound 2 is more generic, all right? It is still the sum of a whole bunch of variables, but and it could be a binomial. A binomial certainly fits this, but it doesn't have to be. The characteristics are, all of t1 through tn have to be mutually independent. They are in a binomial, but again, it doesn't have to be binomial. All the values of t have to be between 0 and 1. They could be between 0.5 and 1. They could be anywhere between 0 and 1, but they have to be bound between 0 and 1. Okay, binomial fits this, but it's not the only possibility. But anyway, those are the extra conditions that you need. Chebyshev doesn't require that, so you can't rely on Chernoff all the time, right? But it has to have mutually independent. Anyway, t is the sum of all of those, and you take the expected value. Okay, you take the expected value of t, and you ask how many. We're taking t being greater than or equal to some number of multiples of that mean. Okay, c is the multiple. What is it bound above by? It's bound above by e to the minus beta c times the mean, where beta c is this function over here. Okay, we're going to do this. Okay, I know it looks a little scary right now, but we're going to do this, and we're going to do it twice today, and we'll do it a couple more times on Monday and Wednesday. Okay, so the intuition is that you add up a whole bunch of independent random variables, just like you did for Bernoulli or voter polls or whatever, and it becomes like a bell curve. Okay, so it converges to a bell curve. Only applies to distributions of sums of independent variables. The variables have to be between 0 and 1. And it actually doesn't depend on the number of random variables. There's no n in this equation. They're individual distributions or they're individual expectations. You actually don't have to know the distributions of any of them, okay, which can be an advantage. All right, so let's do this thing for using Chernoff bound 2. So we did Chernoff bound 1, and I claimed for you that Chernoff bound 2 would be worse. Let's give it a try. So we use Chernoff bound 2 for the probability that z is greater than or equal to 3/4 n. And we want it to look like this form. So this is the same as, okay, the expectation is n over 2. So we want multiples of n over 2. How many of them are there? I think there are 3 halves of them, right? So z is greater than or equal to 3 halves of n over 2, which means that c is equal to 3 halves. Okay, so we're going to sub in c is equal to 3 halves into this equation. Okay, and you just need a calculator for this. I'll do it for you, but the math isn't scary besides. Okay, so beta c is 3 halves, natural log of 3 halves, minus 3 halves plus 1. And you stick this in your calculator, and you get a pretty small number. Okay, it's a positive number, but it's a small positive number, 0.1 essentially. So we multiply this by the mean, and that becomes the exponent. Okay, and what's the mean? The mean is n over 2. Okay, so the probability that z is greater than or equal to 3/4 n is less than or equal to e to the minus, okay, we'll take half of this mentally here. So let's see, let's do this in our head, 0.541 times n. Okay, which is still an exponential drop-off as n grows larger. Okay, so let's try some numbers, and I will know how to get both of these on the screen at the same time. Okay, both on there? Yeah, good, all right. Okay, so for n equals 10, the probability is 0.582. Okay, that's way worse than 0.287. Okay, so that's maybe not so good. N is equal to 32. The probability is around 0.177. Okay, again, not as good. Okay, this is 17%. In fact, Chebyshev is winning in both of these cases, okay, by a lot. And let's see, n equals 100. The probability is e to the minus 5.4. So this probability is 0.0045. Okay, which is better than Chebyshev, but not as good as this. Okay. I'm going to pause here for a moment. We'll do one more example after this, but I just want to make sure everybody is okay with what's been stated. Yeah. Oh, so how did we compute expectation of t? Remember the binomial of n fair coin tosses, you're going to get an expectation of n over 2. So that's it. So expectation of t is n over 2. So when we put that in for this, right, I just did the I divided this number by 2 and got that. Thanks for that. Okay. Other questions? Is it good? Yeah? Yeah, why doesn't it depend on the individual distributions? But it doesn't. All it says is that the variables have to be between 0 and 1. So it could be a Bernoulli, which we're familiar with, Or it could be any sort of crazy distribution as long as it's bound between 0 and 1. It could be some sort of shrunken down binomial, sort of shrunken down geometric. There could be a mini Gaussian curve in there. It could be any sort of crazy thing. All we need to know is what the expectation of each of these things are. We need to find the expectation of this. As a total. All right. You don't need to know how they are. In fact, the variance is not even part of this equation, which is pretty cool. Okay, so one common question that I get is, can I use turn-off bound if the individual variables are not between 0 and 1? Then you can, okay? Like say you're tossing dice, okay, so again, you're adding up all the dice, and there's a problem on your 6th assignment where you're actually asked to do that. You can do it, you just have to transform those dice by some linear transformation, like subtract 1 and divide 5 is usually a thing, right? And that'll transform each die roll to between 0 and 1. You can apply the theorem there. Okay, so the point is don't panic. Just do the linear transformation to the space where you can use the theorem, and then transform it back. Okay, so it does have applications to other things besides coin tossing and that sort of thing. Okay, let's revisit this. Okay, so we're going to apply Chernoff to this. So just remember, the old version using Chebyshev, we required 62,500 using this formula. We're going to use the Chernoff bound to get a better bound. Okay, so this thing, we're going to put this is a little bit problematic that we're taking the two sides. I don't have a good solution for this because the Chernoff bound is actually one-sided. Okay, so it's only taking stuff that's, on one side of the tail. So as a punt, we're going to, instead of taking delta to be, the full 1%, we're going to split the delta half and half. Okay, so we'll take the delta to be 0.5% on the top side of the tail. Okay, so that we can indeed use the Chernoff bound. Okay, so we want Sn by n minus p to be greater than or equal to, greater than epsilon, with less than or equal to 0.05. Okay, so that's going to be our goal. Okay, so in order for us to use the Chernoff bound, we need to restate this using some, it's got to be a multiple of the expectation. The expectation is np, right? So Sn by n minus p is greater than or equal to epsilon. We can just rework this equation inside. Let's start by multiplying both sides by n. So this is equal to the probability that Sn minus np is greater than or equal to n epsilon. And toss the np onto the other side. And we need to find a c so that when we multiply by the expectation, we get this np plus n epsilon. The expectation is np. Okay, so this is the expectation of Sn. And we can, it doesn't look like there's a common factor there, but we can force it. We just divide everything inside there by np, so that over that is 1, that's easy. This is, the n's cancel, this is epsilon by p. Okay, so this is our c. Okay, so we apply the Chernoff bound. We say this is less than or equal to e to the minus beta c times the expectation of Sn. Okay, and I'm just going to draw, both of these. Okay, so I'm just going to draw this over here. What is our plan? Okay, this is a Chernoff bound. Okay, the expectation is np. Pull n people, and each says they like Carney with probability p, np. And beta c is equal to, all right, let's make sure I don't mess this up, c ln c minus c plus 1. Okay, so c is this, so 1 plus epsilon by p, natural log of 1 plus epsilon by p, minus 1 plus epsilon by p plus 1. Okay, so I'll give you just another second to catch up. I know that's a lot of symbols. Okay, yeah. This is Chernoff bound 2, yeah. We can only use Chernoff bound 1 if it's, fair coin flipping throughout. That's the only time. Yeah. So it's almost always Chernoff bound 2, but look for that special case. That special case gets you very, very fast convergence, and you should use it whenever you can. Okay, we're actually faced with the same problem we had when we did the thing with Chebyshev, is that we don't know what p is. P is the thing we're trying to predict. P has a range of between 0 and 1, and it turns out that this quantity here is smallest when P is equal to 1. Okay, so that's the worst we can possibly have. Before we had like a quadratic, right? Here it's a different sort of curve, but anyway, this is smallest when P is equal to 1. Okay, and if you sub this thing in for the epsilon that we want, which is 2%, this gives us a value of 0.0001987. Okay, so that's the end of the box. Okay, all to explain this next step. All right, which is this is less than or equal to epsilon e to the minus 0.0001987 n. And we would like it to be 0.005. Okay, so we can solve that equation. That's pretty easy. Okay, so when delta by 2 is 0.005 n, so we just rearrange this equation. So we take the natural log of both sides and divide by this. Okay, so n will be at least the natural log of 0.005, which is a negative number, okay, because it's below 1, divided by minus 0.0001987. And if you run that through your calculator, you get 26,000. You get a little less than 27,000. Okay, so just to compare what we got from before, right? 62,500. Okay, so taking advantage of the drop-off here got us a better estimate. Okay, so if you're a pulser, you can save yourself, roughly 60% worth of effort. This is probably the best bound that I know of. Yeah, but it's a lot better. Yeah. Okay, other questions? I think it's small. Yeah, you said when it's smallest when it's this, and smaller negative exponents mean bigger overall values, right? So yeah, I think it's okay. So one thing that is interesting about independence, and especially when taking surveys or trying to poll people, is that I mentioned one problem is that people talk to each other, right? Another is, and this usually happens around this time of year when people call to ask me who you're going to vote for. I might not even answer, right? I might just hang up the phone on them. And it might be that those people have specific characteristics, like maybe they all vote conservative, or maybe they all vote liberal, or something. They're shaded in one direction. So maybe you're actually biasing your poll by taking a survey in this way. Speaking of surveys, there's a survey in your inbox right now, and it's a survey. I just want to mention that we historically used to run on paper. Okay, so once a term, we would come in with a bunch of paper, and class attendance was a little bit better than it is these days, but and we would spend the last 10 or 15 minutes of class, and you would each fill out a survey that says how the course was and how the instructor was. And about 7-8 years ago, I think it is, so probably before your time, they decided to switch over, get rid of paper because that was worse, or online surveys are better. And I don't know how you feel about getting surveys, like another notification for a survey. I know how I feel, and I know how I feel when I read surveys about anything, survey results about anything on the internet. Like, have you ever gone to a restaurant based on survey results? Like, everything is either 4 or 5 stars for people who really liked it, or 0 or 1 star for people who have an axe to grind, right? And there's not much in between. And the fact is that a lot of you have sort of average opinions, or slightly above average opinions. You liked it, but you weren't wowed, or you kind of, didn't have a great time, but not a bad time. But it wasn't a 3 sigma event, like nobody, harmed you in doing whatever you were doing. This is a problem because, your feedback matters. And believe it or not, it really, really does matter. I sit on a review committee periodically, so I look at all the course reviews for all my colleagues, and it was my turn this year. I get reviewed every 2 years, and whatever you write on those surveys affects, how I get reviewed. I'm largely a teacher here, I don't do any research. So your feedback is a strong data point, is a strong signal for whether or not I should get a raise, for example. Okay, so what I'm trying to do these days is actually go back to I can't go back to paper, but I actually do want to set aside class time for you to fill out the survey. Okay, this is it. This is today. For those of you who are not here and listening to this as a recording, I can't force you to do this, but I really do want you to spend the time. It is important. Even if you don't think so, it is important. All right. So I'm going to ask you, please, right now, in the last 6 or so minutes of class, please open up your device, go to the login page for the Blue RA. There is a link in your inbox. And I'm pretty sure most of you haven't done it. There was only 6 respondents as of this morning. So please take the time right now to fill that out. Say that again. I'm going to say no. So just hang tight for 5 minutes. So usually it's like the course experience survey. It should be in your SFU mailbox. Is that right? Ah, Canvas. Yeah, there might be a tab in the bottom, one of the tabs near the bottom. That's right. I think I saw one of those. So try there. Sorry, I was thinking of linear regression, which is or curve regression. Okay, thank you. Okay, so I appreciate you taking the time today to do that. A note about next week, I've got about 2 lectures worth of stuff left here, but you have everything that you need to do your 6th assignment. Okay, so the Journathon is the last thing that you need to complete your 6th assignment, but I still intend to prove this and do a few examples next week and some other